So today we are running an IRT and R. IRT is a theory for how people respond to items. So I actually did a dichotomous IRT and I had 1,000 people in my sample. Here's the data. 0 represented that they got the item wrong, while 1 represented that they got it correct. There are 5 items for my test, 1,000 people, and I used the LTM function to do my IRT and R. There are a couple different functions you could use, but I used LTM. So first I installed and libraried it. I then loaded my data set right here, and then I created the parameters for my model using the, well, right here's where I looked at my data set if you'd like to see it. But I then created the parameters of my model using the LTM function. Z1 indicates that I have one latent variable that I'm predicting. IRT.param equals true gives me my output in ABC format. So difficulty, discrimination, and guessing. We're actually not going to have guessing in this one. I'm just doing a 2-parameter. But if I didn't do param equals true, I would get my output in slope-intercept format. So we ran it, and as you can see, it's over here. And it has all 5 items, and has ability on the bottom and probability on the left side. So difficulty is down here, which is the ability B or theta, and that is where does the item best measure the participants, while discrimination is actually how well does it measure the participants at the points, or how good the question is at figuring a person out. So next we're going to do summary. And summary actually breaks the items down by difficulty and discrimination, but it's on top of each other. As you can see, here's difficulty, here's discrimination, and that's kind of difficult to read. So if I actually do the coef, which stands for coefficient function, it's going to be side by side, which is much easier for me to be able to read. So looking at my difficulty output, all of my items are pretty easy. Ability is z-squared, so 0 is actually average. Item 3 is the most difficult on my test with a 2.90. And item 1 and item 0 are pretty average items, while item 2 and item 5 are the easier items on my test. And if I had an item with -3 for difficulty, that would mean that it was a very, very easy item that was actually 3 standard deviations less than the average. But I don't. So my most difficult item, by the way, once again, is item 3. So next I'm going to look at the discrimination values, which is how good the question is at figuring out people below and above the difficulty parameter. And we would like for these to be above a value of not 0.1, just 1, above a value of 1. My items are not the best, as you can see, they're not discriminable. Range of +1 to 4 is the range I'm looking for, but mine are actually negatives, and so that just means that they do not have very good discrimination. So next I'm actually going to plot the model, which gives me this, which was already here, but it's going to plot all the items at once. This is actually the ICC, or the item characteristic curve, and this helps me to see why my items aren't necessarily the best. The ICC is a mathematical expression that connects a subject's probability of success on an item to the trait measured by the set of test items. So I'm looking for an S-shaped curve when my items are plotted. The y-axis is my difficulty slope, while the x-axis is my theta or ability. As you can see, I do not have any S's here. I actually have one that's kind of a negative, or a opposite of the S, excuse me, for item 2. So I'm going to first look at the 50-50 point line to see at which point the line crosses the 50-50 probability of the participant getting the item correct. So that's right here is where I'm looking at it. Say there was a horizontal line right there at 0.5. That's what I'm looking for. So for item 1, the 50-50 point is about average. So right here. Item 2 is actually quite the opposite of what we'd like to see. Like I said before, we want the S going the other way than how it is right here. The 50-50 point line for it is about -1 ability, but people with less ability are actually more likely to get the item correct than people with more ability, which is not what we would like to see. This is actually the same for item 3 as well. It's actually harder for people with more ability, and item 5 as well. So that is not good. That's not what we want. So item 3's 50-50 points is about 3, while item 4's is at about 0 again, and item's 5 50-50 point is at about -2. So the only ones that actually have positive slopes are items 1 and 4, and so that means that the probabilities of getting it right actually increase with the ability, which is what we would like to see. So another way I could have looked at this 50-50 line, which would probably be easier, is if I did them one by one. So here's just item 1 plotted, 2, 3, 4, and 5. So that is how we plot them one by one. Next, we're going to look at the test information function. So it takes all 5 items and figures out the probability for each point among ability. You're hoping for a normal distribution, which I did not get. It tells you where you have the most information and like what your test is really getting the most information, what ability point. So it tells you, the most information about participants. So mine is actually centered over -1 or 1 standard deviation below the mean right here. And once again, we want a normal distribution. Mine is not helping me to determine much from this test since I'm getting very, very little information about people below -2. So down here, as you can see, I'm not getting any information, really much at all. And above 0, I'm not getting much. So I'm only getting information about people that are about a -1 ability. So next I can look at the factor scores. And this is every single combination of response patterns. So there's 32 possible combinations that people got in my data set. So number 1 is someone who got all of them wrong. There was actually 25 of these people, and we would have expected for 36 of people to get all of them wrong. And we estimate that they have an ability score of about 0.17. So that's our expected ability for them. But then if we look at the response pattern for 2 and 3, we see that in both cases, the person only got 1 item right. So for 2, it was item 5, and 3 was item 4. But one of them has a expected score of 0.01, while the other has a 0.27. So this tells us that item 4 is actually more difficult to get correct than item 5, and that's why their ability score is expected to be higher. So next I can look all the way down. We'll see all the different combinations. Factor scores just give you the pattern of the data and what you would expect the ability score to be given that pattern of data. And next I'm actually going to look at the person fit, which is very similar, but the person score gives you the pattern of data and what I would have expected the factor to be depending on that person. So it's slightly different from factor scores because factor scores are about the patterns of the data overall, while person scores are about the person's patterns of data and their corresponding ability estimates. So these imply different things based on the overall patterns versus each individual person as an actual pattern. These scores here are an estimate for a particular person or any people who score this way on a test. So for number 1, it's anyone who scores a 0 on the test. And the output's read as the same before. So for person 1, they got no items correct, and you're going to look at the LZ column for interpretation. Next, I'm going to run the item fit, which is gives me a chi-square statistic for each item. With very large samples, your items are always significant, but you don't want them to be. You're actually looking for a non-significant chi-square. But much like in a structural analysis, the sample size biases the chi-square, so people don't take these values too harshly. And instead, we focus on the A and B parameter estimates that we saw at the very beginning. So just overall, my test is not very good, and it's not very difficult, and it does not discriminate.